All right, next I'd like to use the gravitational force as a centripetal force. So we've seen so far then that you can use a normal force as a centripetal force in the space station problem. We saw that you can use the components of the normal force in the banked inclined plane problem to be your centripetal force. We've also seen how the force of static friction can be your centripetal force in the flat race car track problem, and also as a component of the static friction force in the banked inclined plane problem with friction. We've also seen that the centripetal force can be a tension in a string. But we can also use gravitation. And so this is the subject of chapter 13. And there are just some sections of chapter 13 that I've outlined for you in the Week 5 homepage that you need to worry about for our next quiz. Newton's inverse square law of gravitation is basically the magnitude of the force is equal to a constant. And this constant is called our universal gravitational constant, multiplied by the product of the two masses in kilograms and divided, this is very important here, by the distance between the centers of the masses squared. Okay, so this is a very powerful distance dependence on the gravitational force. So these two masses could be tennis balls out in free space, or one could be the moon and one could be the Earth, or one could be the Earth and one could be the sun. And as long as they're two different masses, then we're just going from the center to the center. And because of Newton's third law, the force of m1 on m2 is the negative of the force of m2 on m1. So that's why I'm saying here the magnitude of the force equals this. But the force always acts in a direction that makes it an attractive force. So that m2 is pulled toward m1 and m1 is pulled toward m2. Now, we call it an inverse square law because it depends on 1 over r squared. And so if we were to increase the distance between any given two masses, so we're not changing the mass, but we just change the distance to, let's say, 2r, then I think that we could all agree that the force of attraction would be diminished because they're farther apart. Okay, so I'll call this F2, this F naught. But how much diminished would it be? Well, here, if F naught is equal to g m1 m2 over r squared, then F2 would be equal to g m1 m2 divided by 2r squared, because we've doubled the distance. And so that'll be, well, 2 squared is 4, so that's 1/4 times g m1 m2 over r squared, or that's 1/4 of F naught. Okay, so anytime you increase the distance by some numerical factor, the force will decrease by that factor squared. Okay, and if you bring masses in closer together, the force will increase by how much you bring them together. So if we go from r to r over 2, then this would end up being 4 times bigger than F naught. And that I'll leave as an exercise for you to show. Now, one particularly interesting example of this is where we have one of the masses being the Earth and the other one being the center of the mass of your body, around the middle of your body. Okay, so let's say that this is mass of the person, this is mass of the Earth, then the radius here, r, is going to be basically the radius of the Earth plus 1/2 of your height, which is essentially the radius of the Earth. Okay, so we'll just call that distance from the center of the Earth to the center of your body the radius of the Earth. Then the force that you feel in this case is your weight. Okay, and so let's just work this out, knowing that the mass of the Earth is equal to 6 times 10 to the 24 kilograms, and the radius of the Earth is equal to 6370 kilometers. Okay, now kilometers isn't the right unit here, and so if I gave that to you on exam looking like that, you would want to convert that to meters before you would go any farther with it. But let's figure out then how that would work in this special case situation using this value for g. It's a very small number, this value for g. We don't know why it's so small, but this makes gravity the weakest of all of the forces. And so this is experimentally determined to be this very small number. But if somebody tells you they got knocked off a roof, you go, well, the gravity didn't feel so small to me. But in relationship to, say, the electric forces, if I take this pin and I drop it down onto the table, it's the whole Earth's mass that's pulling on this pin. But what's stopping it is just the electric forces from a few of these atoms that are right nearby. And so those few electric forces are balancing out the weight of the whole Earth pulling on this thing. And so if you think about it that way, the force of gravity is pretty small in comparison to the other forces. So going back to this problem then, let's say that your weight then is equal to g times the mass of the Earth divided by the radius of the Earth squared times the mass of the person. And if we write it this way, we're breaking up the inverse square law into this times that. Then we can multiply out these numbers. This gives us 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by the radius of the Earth squared. Now here, let's just convert this. So this is 6370 times 10 to the 3 meters. And so that's going to be 6.37 times 10 to the 6. 6.37, bring this over 3 decimal places. That gives me another factor of 3 there. And so then this is going to be the radius of the Earth in meters, and that'll be squared. And that's times the mass of the person. Okay, so I'm breaking it up this way because this combination of constants all multiplied out gives us 9.8 meters per second squared, which is the acceleration due to gravity on the Earth. So it's 9.8 times the mass of the person, or mg. What this tells us is that if we were to go a certain distance away from the Earth, let's say you could climb a ladder, and that ladder were the radius of the Earth, which is about, well, it's 6370 kilometers. That's about 4,000 miles. So if you climbed another 4,000 miles and then stood up on the ladder and stood on a scale here, your weight would only be 1/4 of your weight on the surface of the Earth, because you'd be twice as far away from the center of the Earth at that point. Now this would be a very hard thing to do. You need a really strong ladder, and also there's a lot of space junk right here. The atmosphere would be over with about the thickness of this pen on the scale of this drawing, but you'd also be getting hit by space junk. You'd have to be dodging that, moving about 5 miles a second. that stuff could go right through you. If you could get through that, then you'd need oxygen, but you'd eventually get up to this point, and it would be easier to climb the ladder later on. And your weight then would only be 1/4 of your weight on the surface of the Earth. So that's the way that the gravity force works in terms of the inverse square law. And we'll do more with that when we get into more detail with chapter 13 in a later section. That the part of chapter 13 that I'm interested in you being able to work with is the part that just deals with uniform circular motion, because that's what we're doing right now. And gravity is one example of that. So if we just look up at the data projector for a second, we can see, first of all, this is the plot of the force of attraction between two objects as a function of distance. And it goes like a 1/r² plot. So if you double the distance, that's 1/4 of the force. Triple the distance, 1/9 the force. 5 times the distance, only 1/25 of the force. And so here we've got a planet being pulled toward the sun by the gravitational force. And that will change the planet's direction. And so therefore becomes a centripetal force. We can also see in this kind of a problem that orbital motion really is a balance between inertia and gravity. Because if we were to throw an object with a speed that isn't high enough, then it'll kind of curve around the Earth to a certain point. But only if we give it just that critical amount of speed, which turns out to be about 17,500 miles an hour, about 5 miles a second, will this object move horizontally and then fall by just the right amount so that it stays in a circular orbit. So in other words, the inertia keeps carrying this thing at along a path that is tangent to the path, but then the gravity force keeps pulling it in. So if you turned off gravity, this thing would just keep going in a straight line and get farther away from the Earth. But because of, and just gravity, it would just fall toward the Earth. But with inertia and gravity, you can balance this out just perfectly so that your horizontal or tangential velocity can just compensate for your falling motion. So essentially then, an object that's in orbital motion is in free fall. Say this is the Earth, and this is you in orbit in a satellite. So if you're moving this way, in 1 second, if you're moving 5 miles a second, in 1 second you've moved essentially 16 feet farther away from the Earth because of your tangential motion. But because y equals 1/2 gt squared, 4.9 meters is about 16 feet. So that's how far you fall in 1 second. So you go 5 miles, fall 16 feet. 5 miles, fall 16 feet. 5 miles, 16 feet. 5 miles, 16 feet. 5 miles, 16 feet. All the way around. And if you, in 90 minutes, that's about how long it would take for this object, if it were close to the surface of the Earth, to go all the way around and come back to its starting point. You threw it from there, then at that point you'd have to duck because it could hit you in the back of the head. Okay, so that's why we say that this orbital motion is uniform circular motion with a centripetal force that is the gravitational force. And it's a balance between inertia and gravity. So this is our force. Let's say this is the sun. This is the Earth, not to scale at all. Let's find if the distance from the Earth to the sun is 150 million kilometers. Let's find the velocity of the Earth's orbit. And we'll be given some facts here. Let's say the mass of the sun is 2 × 10⁻30 kilograms, and mass of the Earth is 6 times 10 to the 24 kilograms. Okay, so we're given those facts, those pieces of information, and also the distance from the Earth to the Sun. This is the same thing as 93 million miles. Okay, and what we're trying to do then is find how fast the Earth is moving in its orbit around the Sun. Now here we are assuming that the Earth is moving in a circular path. That's not exactly true. The Earth has a variation, what's called an ellipticity, of about plus or minus 2%. When it's at its closest point of approach, it's going about 91 million miles away. When it's at its farthest distance away, which is around the 4th of July, it's going 95 million. It's 95 million miles away. And so that averages out to 93, which is the number that we'll use here, because it doesn't vary that much from a perfectly circular orbit. And so we can say that the sum of the inward forces, okay, inward then is toward the center of spin, which in this case is from the Earth toward the Sun. So sum of the forces inwards equals mv squared over r. But which m? Is it the Sun's mass or the Earth's mass? Well, if you think about it for a second, you'll realize that what is moving here is the Earth. That's what's feeling the centripetal force from the Sun. So this then must be equal to the Earth. And then we'll set that equal to the gravitational force, which is g times the mass of the Earth times the mass of the Sun divided by the distance between the Earth and the Sun squared. So we can see then that by writing this correctly, we cancel out the mass of the Earth. And that tells us that any object at the Earth's distance away from the Sun that is moving with the same speed that the Earth is moving with would be in the same orbit that the Earth is in. Okay? And so the Earth's mass cancels out of the equation. And so we didn't really even need the Earth's mass for this problem. I just gave it to you because sometimes in a real life problem you're given more information than you need, and you have to decide what to get rid of. Okay, so here if we solve this for v, that's going to give us the square root. One of these factors of r cancels. That'll be the square root of g times the mass of the Sun divided by the distance from the Earth to the Sun. Okay, so here we're not talking about the radius of the Earth anymore. We're talking about the distance from the Earth to the Sun, which is 150 times 10 to the 6 kilometers. Now we're going to need to write that in the correct units. So we could write this in as 150 times 10 to the 9 meters, or that's 1.5 times 10 to the 11th power meters. And then we'll plug in for the mass of the Sun, then we'll pop in that g factor. Be sure not to confuse that with the acceleration due to gravity. This is big G, not little g. Big G is our universal gravitational constant. So that's the square root then of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Sun, 2 times 10 to the 30 kilograms, all divided by the distance from the Earth to the Sun, which is 1.5 times 10 to the 11 meters. Crunch that out. That gives us approximately 3 times 10 to the 4 meters per second, or that's about 30 kilometers per second. If we convert kilometers into miles, that gives us something like 17 miles a second. So that's how fast the Earth is moving in its orbit around the Sun, about 17 miles a second. And so if that's the case, and you were to say, do some time traveling, where you had a time machine and you wanted to go into the future, you also have a more difficult problem of figuring out where the Earth is going to be at that future date, because it's not going to be here anymore. The Earth is going to have left this location in space far behind. And also, it turns out that the Sun and our solar system orbit around the center of the galaxy and are moving at a speed of about 140 miles a second while it's doing that. So there's all kinds of motions, almost enough to make you dizzy, except for the fact that the accelerations are low enough that we don't feel them.